consultant of geostatistics at Geovariance since 2019. Today, in the framework of the webinars to present our products and the services that we have that we propose to the industry, I'm going to talk about the classification of mineral resources using the Kriging results and also the other geostatistical tools that we have. Hope to be helpful for you and to give you some insight toward what we can do based on the geostatistics in for the mineral resource classification. Well, the presentation takes about half an hour. I will answer your questions if you have at the end of the webinar. Meanwhile, when I'm presenting, don't hesitate to write your questions in the chat, in the conversation, as your friends has already done it. And you will receive the video by tomorrow if you want to have it or to share it with your colleagues, with your friends. So it's possible. Let us start with some basic definitions about resource classification. When we talk about resource classification, in fact, we want to give a confidence to our interpolations. We use different interpolations or different procedures, different workflows in order to interpolate the mineral blocks. Interpolate, for example, in this image, you see that the iron value is interpolated for different blocks based on the drill holes that we have on our deposit. The next question is that what is the confidence of this value? Because the interpolation is different from the measurement, and when we are far from the drill holes, for example, in this area that we don't have close samples, of course, that we have less confidence than another estimation, which is in this area full of samples. And also, it will become more important for us in case of extrapolations. For example, this tiny block very far from the samples, of course, that we have much less confidence about this estimation that we have done. So we want to categorize, in fact, all the blocks in 2 or 3 categories. Classically, we have 3 categories: measured, indicated, and inferred. Inferred has the least confidence and measured the highest confidence. So as a result, in the mining industry, the measured will be produced before inferred, because for the inferred or for indicated, we have more uncertainty or less confidence about our estimation. And for our measured blocks, we are more certain, so we can do planification on the measured blocks. And as you can imagine, it concerns about the investment and about the mine planning, which should be taken into account. The first organization who proposed classification of mineral resources is the JORC. These days, the JORC is also already integrated in a more international entity called CRISCO. So JORC or CRISCO, they are responsible for defining, or they initiated, in fact, especially JORC, the defining or proposing this classification for the estimations in order to be sure about the measured class, and we have less certainty about the inferred class and middle certainty for the indicated. The JORC or CRISCO reporting codes, they are highly dependent on a competent person or qualified person who has some characteristics, like, for example, having more than 5 years of experience in the same mineralization type and in the same activity. So you can see that in the classification of mineral resources, there are some subjective part. Of course, it's professional, but subjective to some extent. And it's based on the judgment of a professional. What geostatistics provides is providing some criteria, mathematical criteria, that help the CP or QP in order to do this classification in a more objective way based on some geostatistical or mathematical criteria. And what is very important for us in geostatistics is, of course, variogram that explains or quantifies the spatial continuity of the deposits. So the proposition of the geostatistics is not only more objective, more mathematical based, but also takes into account spatial distribution or spatial dependency or spatial correlation, or for example, the anisotropy of your mineral grade. Let us verify quickly what are the previous methods that used to use that the experts used to use in the previous years. This is another example of its of estimation. The color scale is different from the previous one. That's important. Or maybe it's another slice because it's a slice view, so it might be at different altitude. Oh, we define different passes for during estimation. One of the passes is the smallest one, the standard one. The small pass means that in the areas that we have some restricted neighborhood definition, the blocks which are far from the data will not be estimated. And then for the four blocks where we are farther from the drill holes or from the data, we will make a bigger neighborhood for the estimation, and we will define a less certainty or less confidence for the estimation which is done in the yellow blocks, and even less for the orange and much less for the red ones. So it's some sort of classification based on neighborhood or based on distance. Such methods are very useful methods because they were at least based on the distance. But the inconvenience was that it takes into account the distance, but it doesn't take into account the spatial variability, or for example, the anisotropy. It means that the distance in a horizontal direction and the distance from in the vertical direction, or in the northward, in the southward, they have the same impact for the classification of the resources, which is not good because as a geologist, we know that the variability of a phenomenon, of a geological phenomena, along vertical is usually higher. Why? Because we have, for example, stratification, or we have some other phenomenon that vertically causes more variability, and horizontally or in some direction we have more continuity because of the simply mineralization processes. So using geostatistics helps us in order to integrate such complexities in our mineral resource estimation. So in one direction we will have more elongations, and in another direction we have less. Second point is something that I tried to explain, that the previous or the distance-based criterion ignore the spatial correlation or the anisotropy, that we want to reproduce it based on geostatistical and more advanced tools. Just after the development of geostatistics, which backs to 1960s, we have a definition of a function called variogram. Variogram measures spatial variability as a function of distance. So it's in fact a converter. It converts the distance to variogram value in different directions. And having this quantity helps us in order to define standard deviation of Kriging, which is a stochastic parameter of estimation accompanied with the estimation. So geostatistics proposes us not only the estimation, but in parallel associates directly a standard deviation. This standard deviation is a measure of uncertainty, lower uncertainty close to the data, higher uncertainty far from the data. And this value has a physical sense for us. The physical sense is that since it's a standard deviation, it has the same unit as our grade. If it is in ppm our grade, so this standard deviation is ppm. If it is in percentage, it will be in percentage. If it is in ppb, it will be in ppb. If it is in count, it will be in count. So they are related. It has some physical sense for us. And you can naturally imagine that we can apply different thresholds to this standard deviation in order to categorize. Still, what is the threshold? We need initially we needed the CP to define it. In fact, when we estimate mineral resources based on Kriging method, for example, in the software of Geostatistics that we promote, meanwhile, you will have the Kriging output. You will have about 10 or 11 other criteria. So we have one estimation for each block, one estimation value, plus 11 or 10 or more measures or criteria of error. So we have several error criteria which are all calculated for this block. And based on these values, these criteria, we will provide some or we will evaluate or classify the confidence of the estimation. Do we need to study all these 11 variables, which are quite a lot, to study all of them? In fact, no. Why? Because some of them are correlated. They are correlated, but some of them, for example, have the different ranges. Some of them have different scales. So they are in different scales. So we have to use them wisely. No need to use all of them together. I will show you some examples in this webinar, but the details are mostly in the mostly discussed in the trainings. For example, look at standard deviation, which is here, and we have also shown it in the previous slide, and the variance of the estimator. We can plot these two, and we'll see what is the behavior between standard deviation and variance of estimator, that it shows such complex behavior. And if I add the neighborhood classification on this image, you will see that the green part, which is close to the samples, it has higher variance of estimator and lower estimation Kriging standard deviation. And the red one comes here, and also we have a strange part here. So I can in fact divide it to two parts. One part, if I have my pen, I can show here. One part which is here, this half, you have some understandable negative correlation between these two variables, and this part that I'm going to show it by a cross. There's a part which are very far from the data. Either we are in extrapolation or we are simply far from the data, and it's when I'm using far, how much is far is defined based on the variogram. So we will have some idea about the quality of the estimation. And if I want to explain more in the EDA, in the exploratory data analysis, we can have some interactive images. So I have in fact highlighted this half of the plot, and you can see that all the highlighted blue blocks are in the extrapolation zones. So they are either in extrapolation zones or, for example, at the bottom where we have less data. So simply based on this cross plot, we can at least separate the extrapolations, and we know that the extrapolations should be reported as inferred, not as indicated or not as measured. Let me introduce you to another method that we have in Geostatistics software, and it's an interesting method that I like to present it to you, especially. It tries to imitate the simulations. So it has some advantages that in case you cannot apply the simulations because of the memory issue, or because of the time issue, or because of some hypothesis that you cannot apply for Gaussian transformation. So SSDV, in fact, can help you. SSDV, or spatial sampling density variance, can help you in order to propose a classification in a very quick way and in a very interesting way. I recall that in simulations, if you do simulation on two different blocks, block 1, block 2, block 1 or the green one, the values are very close together. So if I do a histogram of the scenarios or of realizations, you will see that we will have a very narrow PDF. And for the block 2, we will have a bigger standard deviation. Both of them have the same average. The average is 20%, the estimated value 20%. But the standard deviation for one of them is narrower, for this one is narrower, and the standard deviation for this one is bigger. So we don't have the same confidence for B1 or B2. Maybe I guess that the B1 is between the samples. I have many samples close to B1, and I guess that the B2 is another block which is far from the samples. So the samples are either far or we are in the extrapolation. So in this case, what we do, simply we calculate the standard deviation, and it's possible also to calculate the probability of having the realizations in the 20%, which is the average, plus and minus 15%. 15% of 20% is 3. So it will be between 17% and 23%. So if more than 90% of the realizations of the scenarios proposed by simulation are in this area, usually we consider it as measured. Of course, that the CP or qualified person might change the values locally for different mines, depending on the tolerance that your factory can accept. So it could be optimized too. But in a general term, we usually use that only 10% of the scenarios could be in the dark part, and more than 90% should be in the white part in order to classify it as measured. It means high confidence. But if you don't have 90% of the realizations in the white part, but still we have more than 75% in the white part, we can imagine it as indicated. It means that less confidence. And if the number of the realizations who are in the white part are less than 75%, we will consider it as inferred. About the basics, again, we'll talk about it in detail during the trainings. 3 days of training for mineral resource classification, or 2 days and a half. I will show you at the end on the website of Geovariances how you can reach to the details of the training, which is adapted to mineral resource classification, an important step in reporting mineral resources for the CP. And there exists a classical method which is developed by Materon in 1971, called Global Variance of Kriging, and its development in 2016 by Jacques Riboira and Didier Renard, the professors at the School of Mine, Paris School of Mine. Paris School of Mine is the cradle of geostatistics since 1960, and still they are participating in the development of this branch of science. It's this branch of statistics, to be precise. So in 2016, they proposed SSTV. SSTV is some sort of calculating the density of the samples, or how many samples are in different locations. And based on this theory, we can calculate these maps. The first one is SSTV, and you can see that the values are lower close to the samples, and they are higher far from the samples, or in the areas that we have less samples. And the problem of the SSTV value, the first development of this method, was that the unit is very complex and does not have any physical sense for us. So the researchers converted these astronomical values to more comprehensible values, which is called specific volume. Specific volume is the volume which is attributed to each sample. We can imagine it's something like this. So if we have more samples in one area, less volume is attributed to each sample. If we have an isolated sample, we will have a bigger volume which is attributed to this sample. It shows higher uncertainty. Again, specific volume or specific surface, because if you do your estimation in a 2D way, we can call it specific surface. Specific volume and a specific surface, it has a unit. It's more understandable for us. It has a physical sense, but still we were interested in using coefficient of variation. Why? Because the coefficient of variation is something very similar to the output of the simulations. If I come back to this slide, for each simulated block, you have an average and a standard deviation. And dividing the standard deviation by the average, we will have coefficient of variation. And this coefficient of variation, we have the habit of using it in the mineral resource classification based on the simulations, and we have the thresholds to respect it and to classify the mineral resources. So based on SSTV, without doing simulations, we can have coefficient of variation, and we already know some useful criteria, useful thresholds based on the rule of the thumb that proposed here, or you can calculate the other thresholds based on the other percentages that you want in order to classify your resources based on the CV calculated by the method of SSTV. So here, as you can see, based on the CV of SSTV, we can generate the measured, indicated, and inferred resources at the different slices, depending the different slices, different altitudes. And also it proposed us the possibility of including the production volumes. In fact, when we produce more annual production, for example, or quarterly production, it means that we will have more mixing phenomenon. When we mix more the data, it means that in fact we are producing the high grade and the low grade together. So the average is going to be the average of the production will be closer to the global average. So we have more confidence about the grade value when we are producing more higher volumes. So in this case, we will have an impact of the volume on the CV. So if you have less production or if you have higher production, the CV will be changed. And in fact, the production is linked to our classification. It's possible to produce different tables for different cutoffs, cutoff 0, 50, 60, different tonnage or quantity of the metal, and the mineral grade average. Let me open Geostatistics software in order to show you what are the steps in this software that we want to promote. So here is the project manager of Geostatistics. I prepared this example for our mineral resource classification. I think you already know the different parts of the Geostatistics. Very quick introduction. So at the top we have a black ribbon that contains the home for import or export the values. So here we can import or export the drill holes, for example, or the grids, or even you can create the blocks here. Also at the end, we can export the blocks. We have a 2D view, a very useful 2D view that I can show you, for example, the drill holes, or it's possible to change the color of the collars, or adding, for example, some label like the drill holes and the background and also the framework, changing it to here. And it's possible to have an in-depth view. So I can show you, for example, what's happening here between these three. Simply, there are the logs that I need to define some tracks. Very usual in the softwares like this one. If I visualize for you, for example, the iron. So it's the iron in depth for these three wells. And also I can add another track, for example, the track of I don't know, final lithology maybe, or I have maybe a simpler one, iron or rich. I think it's not too bad. No, it doesn't have very much colorful. I prefer to find something a little bit more colorful. Why not? Finally, okay. So let me synchronize the depth to be able to compare or to correlate the wells. So it's interactive. I can choose these two to see what's happening between these two. You see the ore rich part and also ore poor one. It's possible to zoom in and to scroll or simply add, for example, these two or add this one to have the third one. And in Is It Snow, I can send it to report. If I send it to report, in fact, I will have every information here. It's a report of Is It Snow, so you don't need to go and return with your Word or other softwares. You can prepare your report of resource estimation and classification prepared by Pedram, February 2025. And you can add your report here, add your graphics. If you want, for example, to add a histogram of your iron, the composites of iron, it's possible to do a histogram here. That's all. And if you want to apply some selection, for example, only in the rich ore, so it's a histogram only in the rich ore. Number of classes, I will reduce it to 10, for example, or 20 was good. And lower bound, I don't need 30, maybe 40 in this deposit. So send it to report. That's all. You have it here. What else we can visualize? For example, the grids. Here I have visualized the result. Let me first of all visualize for you my estimation. My estimation for the iron, the first estimation that I can show you is inverse distance. Why not? It's the inverse distance. And it's possible to do a section. So here I'm doing a section. You can do also define a kink section, or you can walk inside your mineral resource to see what's the behavior of the grade spatially. You have a very dynamic EDA that helps you to see to analyze the data and do very graphical analysis. It's not the main topic of today. I've prepared something for classification. Let me follow my classification workflow. It's a simple workflow that I wanted to do it together. So from statistics, we have an exploratory data analysis that if I open it, I can, for example, visualize iron in 3D. Here is my visualization. Let me change the color to be able to be easier for you to follow. And you can see the samples. And what are these curves, these graphics? They are the variogram, horizontal variogram and vertical one, and both of them together. We can visualize the directions. So if I click on this icon, you can see that I'm doing very graphical analysis along the red direction. So this red direction is the direction of this variogram, and the blue one is the normal to this reference surface. The details are specified here: the dip azimuth, and the pitch, 15 to 70 and 150. Let us save it to save my variogram. The details of the variographical analysis, we talk about it in MRE course, MRE training, mineral resource classification, mineral resource estimation. And we can do estimation based on the Kriging. So the Kriging panel, you can find it from here. Based on the variogram that we have defined and the output, which is my block model, we can do Kriging. I will not enter to the details. The details, we have some, for example, neighborhood details. So one of the things which is important for us is the radius of the search, which is defined here 170, 150, 150, 30. So for the blocks which are close to the samples, we will have the estimation. For some of them which is farther, I will enlarge the radius that I've multiplied by 2 to be able to find the far samples. And if, for example, for the orange blocks, we don't find even in the radius of 300, 360. So I will make it larger, 450, 450, and 90. So as you can see, Based on the distance from the wells, we will have different sizes of uh, ellipsoid of search, and the colors which are attributed in order to do um, classification of the resources based on neighborhood. Next, and run. If I click on run, it will calculate, estimate, and results, and the results are here. It's possible to visualize the result in depth. For example, if I show you the neighborhoods that I have, it's not this one, neighborhood index. So the green one is standard, which where we have more data, and yellow one we are a little bit farther, and the orange and the red one, they are very far from the data. So we have less confidence over there. So it's a classical way. Then based on a calculator, so we have a Python-based calculator that you can calculate some criteria. I'm not going to the details that where does these equations come from, because they need some more complete training. So I defined RKV and SRKV. Let us visualize them at least to see what is RKV. RKV. So you have more blue colors close to the samples and red colors far from the samples. And also it's a squared one. It's simply a square which is applied to it. And it's more interesting to see it in EDA, because in EDA we have an interactive space that if I show you the number of the neighborhoods, the number of the samples which are calculated, which are used in the estimation versus the SRKV, and it's possible to, for example, visualize the far samples. They are here, the blue ones that I have highlighted. They are either in the extrapolation or at the bottom where we have less samples. In fact, they are the mineral blocks. And the threshold is CP who can propose the different thresholds on the SRKV in order to propose a classification. So more restricted if you use the shorter, smaller threshold, and uh, you will have, depends on the exigence of the uh, of the usine, of the factory, you can change the cutoff. This is the diagram that I showed you just before. And based on this diagram, which is the variance of estimation versus the variance of Kriging, it's possible to visualize where we have weak estimation and where we have good estimation. So I highlighted the weakest estimation, which is again at the bottom or at the extrapolations, and the good estimation, which is in the central part of our mineralization. Again, you can apply different cutoffs or multivariate cutoff. So if I used, for example, like this, I'm applying, in fact, the multivariate cutoff to show you the best part of the measures. It's possible to apply the cutoffs. For example, presume means inferred, indicated, and measured based on the cutoffs that I used manually myself. And if I show you the classification, which is done based on this method, this classical method, it's quite classical. It will be like this. So here are the classification. We can see that the green part are usually at the surface, and the red usually at the bottom, and the yellow, which is indicated, is in between. For the simulations, we can do simulation using the Gaussian variable. So the Gaussian anamorphosis is used based on Hermite polynomials in order to define a variogram. And then using the simulations that you can find all the simulations in this part. The first icon, the simulations are for numerical variables or continuous variables like grid. The rest are more advanced and more advanced methods for categorical variables. So we can do simulation for numerical or categorical variable. For the numerical variable, we have three algorithms: TBS, turning band simulations, SGS, sequential Gaussian simulation, and also SPDE, stochastic partial differential equations. And also we have several other options. You can apply the several these options if you want, for example, to include a false in the simulation. I've already done 100 simulations, and based on these simulations, I have calculated the CV, which is the standard deviation divided by average, normalized by average. So we can calculate the CV, which is V2. What is V2? Standard deviation divided by V1, which is the average. And I have calculated some categories. For example, for the quarter production, the thresholds which are used, you can see the thresholds. Why these thresholds are used, there's a tiny mathematic behind. Again, we talk about them during the trainings. So I can create it. And if I create it and show it to you, the simulation based for the quarter would be like this. So again, it's very interesting. At least it's more interesting than the previous one, because it not only takes into account the distance between the samples and the blocks, but also the heterogeneity which exists between the samples. So in the area that we have high number of the samples, but we have high variance or high heterogeneity between the sample values, it will not become green because we have uncertainty about our estimation, or our estimation is in a heterogeneous zone. So simulations, the main advantage of the simulation, which is one of the reasons that we use these methods, is that they can distinguish between high variable and low variable zones, or they can include the spatial variability. And also the last method that I want to show you is this one. In the Kriging panel, we have SSTV option here that you, our clients, you can apply the SSTV, this method, which is a method available for monovariate geostatistical sets. And it's a method which is based on a, we call it a mega block. We need to define a mega block. It's the approximative part of the SSTV. And also the advantage of this method is that you can include the production volume in the estimate, in the classification. So bigger production or more production, you will tend more to the global average of the values, and less volume, you need to have a more precise evaluation of your deposit. Why? Because by producing locally, you will need to have a more precise estimation of the values in order to be sure about the provided or the estimated average about this value, about this for this deposit. We have less mixing issue. In bigger volumes, we have a mixing phenomena. We have a dilution based off mixing from the high grade and low grade. But in a low volume of production, then we need to be more precise in order to have a correct evaluation of our estimation. So as you can see, for each block, for each SMU block, we'll define a mega block or a bigger block, that this big block permits us to calculate this heterogeneity or this standard deviation or this spatial sampling density. It's based on spatial sampling density. So all the parameters that I showed you, spatial sampling density or specific volume or CV, which will calculate it in based on the samples which are in this area. We call them inner samples. At the output, I can ask for having the SSTV, specific volume, and also coefficient of variation. We have some other more classical parameters, and I can show you the results quickly because I have already done it, not to waste for the executions. So it was the quartile of the simulations, and for the SSTV was like this. One of the advantages of the SSTV is that it will have one of the advantages of SSTV is that it will have a more continuous classification. Why? Because it's based on a bigger block which is defined. It's a mega block or it's giant block which is defined on the deposit. It is defined because we need to select the inner samples. And as you can see, it's more simple. It's simpler, and also you can see that the green part or the measured part is mostly at surface, and the red part mostly at the bottom, which is interesting for us. So I can walk like this, or I can change the direction to a little bit show you in this direction. Let me show you the axis so you'll have an idea about the distance too. So in this area, the red area, in fact, we don't have very much samples because they are a little bit far from the drill holes. And the green part, we have more certainty of our estimation. Why? Because we are in the sample zone. And the yellow part, which is indicated, we are in between, not that much certain, not that much uncertain. So we need further sampling and further exploration efforts. That's all that I can show you oh, no, maybe I have another thing. Yes, I have grade tonnage curve, which is our latest development. We had another interface before, but this interface, maybe some of you that you have not yet used the latest version, maybe you're not familiar with this one, which is easier working with it, and also the options are a little bit more user friendly. So you can have the curve of the tonnage, as you can see here is the tonnage versus the cutoff, or the mineral grade, or combination of both of them on the left one. More complex to read, but if you have the habit, why not? And also metal quantity, which is descending. And it's possible to produce the tables. The produced tables are based on the um, inferred, indicated, and the measured for 3 different cutoffs. The cutoffs are defined in this area. We have some nice tooltips in order to help you to complete all these parts here, or for example here, what is the domain, what is the definition of the categories. You can either define based on the cutoffs, or for example in the iron deposits, usually we define based on the quality of the products or the categories. So we can define these tables based on the cutoffs or based on the categories, and also based on the mineral resource classification. That the name here is written categorization. For me, it means a classification. And one new thing that we have added here, look at for example, the metal quantity, which is in megaton. So if you want to define the precision is possible. We can define, for example, 5 precision, but usually in the JORC, we should not report the meaningless figures. So if I put 0, it will round them. And if I put -1, it will round them more. -2, it will round even more. Okay. I think -1 is good in this case to round everything. We can do rounding for all of them, and it's one of the we can round also, for example, the volume. We don't need that much precision, or the tonnage, or for the grade. I used only one figure after the decimal. You can use 0, or you can use 2, or you can round them, but you should not round it here because I think we need at least 1 decimal here. So, that's all that I wanted to show you on the software. I come back to the slides to end at the end, I want to show you some marketing slides. So Geosatistics is an advanced software for geostatistical solution, geostatistical evaluation and analysis. If you want to do some high level and advanced geostatistical estimation or simulation or quantifying the uncertainty, you can use this software, which is a classic in the mining industry. Geovariances, we propose not only different softwares, the old Isatist Neo, which is a user-friendly software that I just showed you. It has mining edition, petroleum edition, and also general edition. Uh, by paying the annual maintenance, you will have access to customer service to ask your questions and also to maintenance. Maintenance, it means that each year we have 3 releases. So each release we have some new features that the developers they add to the software, and also we have some trainings here. I'm in the training and consulting department, so if you need to do some training either on the TS6 or on the application, or if you want someone to accompany you during your mineral resource classification or estimation, or if you have some other requests, we are here, me and my colleagues, to listen to you, to your needs, and to accompany you during your classification or to train you to be independent and to use the software independently for you. Some clients start with asking us for example, for some consulting, then they try to internalize all the knowledge themselves, or some other they want to start from the beginning in an independent manner. It's you who decides. We only accompany you to reach your objectives. What we propose these days is a bundle solution, bundle of Studio RM Pro, that by buying one license, you will have access to 3 different softwares. RM Studio, very famous in the mining industry for mineral resource estimation and classification. Supervisor, a powerful tool for variographical analysis and also for exploratory data analysis. And Isatist Neo that I just showed you, advanced geostatistical tools to complete your workflow of estimation. So by buying one license, you will have access to 3 softwares. A nice solution for mineral resource estimation. These days, geovariances and EZTs, they belong to a bigger enterprise called Datamine, very famous in the mining industry. So there are several other softwares, either in the package of geology or mine planning or exploration. You can see EZTs now, and also EZT.py. If you want to use the Python solutions of the EZTs, it's possible. We have the Python package. It's based on annual subscription, so it might be interesting for you. As you can see, Studio RM, Supervisor, and also the other softwares that you can see, Studio Mapper, Zero Vision, on the Minescape, and also Ore Controller. We are all in the same package. There are also the production, laboratory, and sustainability packages. For more information, I invite you to verify the site of Datamine, or you can simply contact one of our colleagues. That you can see, our offices are in all over the world. So in all the continents, we have the colleagues that can accompany you, or you can simply contact me at Fontainebleau or my other colleagues who are here in order to help you in your own local language, French language, Portuguese language, also Spanish or English. And so here is a small list of our customers that, as you can see, the big mining groups are already our old customers that we accompany them. We have the chance of accompanying them in their nice projects on their mines. It's time for you. I already talked a lot about mineral resource classification, Isatist Neo, Geostatistics. Let me open conversation and see what are the questions here. So in the conversations, after the greetings and some messages from the AI assistants, very nice, AI assistant, AI. Mm. Question of Jafar. Hello, Jafar. Hi, Pedram. Thank you for your explanation. I just want to ask 2 points. How to properly validate when assigning resource classification using conditional simulation. When defining resource classification using simulation, which is more appropriate between work in 2D or 3D practically? About your first question, how to properly validate when assigning resource classification? Mm, in fact, what do you mean by validating? Because, I understand that there might be different criteria. In fact, Geostatistics provides a criteria-based solution. So the criteria which is proposed is from the point of view of mathematics is already validated. What we do in practice is to propose 2 or 3 different classification methods, and then we will discuss together to see whether this method or that method proposes some logical output or some illogical or less logical output in some areas. So it's possible because the methods are not necessarily adapted for all the situations. It's a good idea to use 2 or 3 or more methods. Usually we use 2. In the area that we have converged results, we are certain about our classification. And in the areas that we are less certain, we can start to discuss and to judge. Usually, if you follow all the steps in a methodic way, there is no reason to have deviation. But sometimes we have forgotten, for example, some parameters or some phenomenon. We might have some deviations. So it's good to verify. So in fact, we verify the results in order to validate. But we have to pay attention that if everything is followed in a methodic way, usually we don't have a big issue. So it also depends on the user. The user who has more experience, of course, that he can converge the results easier, and having less experience will make everything a little bit needs more effort and more validation, of course. And about your second question, because a mineral deposit is a 3D 3D phenomena, is a 3D object. So I prefer to use 3D resource estimation. The 2D or simplistic way was mostly interesting previously, that we had less 3D capacities, but these days, based on the capacities that we have in 3D, it's better to usually do the 3D. So in general, I can say 3D, but one day you might argue. Let's move to the second question of the Olivier. Olivier, you have 2 questions. Is Geovariances interested in developing machine learning approaches to classify resources, or potentially to clean isolated artifact created when using a statistical classification like SSTV? Might we also see classification articulated into formal workflow within NEO? In fact, about using machine learning, we already use machine learning. We can use at least machine learning in Isatis NEO. We use it for as demand. When the client asks us, for example, to use this method or that method. Why? Because our calculator is Python based, and we can use sklearn or other packages that you have in order to classify based on the outputs of the geostatistics. So we can use, and we use machine learning in the, also we have a training about machine learning that I want to show you the trainings. Let me open the trainings also. So geovariances. Here's the website of Geovariance. And the training, you have the catalog of the training that you can reach to our all the trainings for example, mining industry. The next one is geological modeling by Geostatistics. It's a 3D course. The DHSA 3D course. Isatis NEO fundamentals, only for us to start Isatis NEO. It's a 1 day. You have several Isatis.py courses. And scripting. Mineral resource estimation is maybe the most important one. A 2 day training for univariate and 2-day for multivariate, and also classification. Where is my classification? Yeah, here is my machine learning, and also statistical inputs to resource classification. So here is statistical input to resource classification that I can share it with you in the message part to read the objective, the outlines, and the next training is in the March 17, 19 that my colleague will present it. So if you are interested in it, do not hesitate to ask for a code online. By asking a code online, you will receive all the instructions. Or if you want, the next session will be in the November. They are the public sessions. We can have a private section if you want for your team members. And also machine learning, if you are interested in machine learning, the next public training will be in April. And also we'll have another one in the September. You can read all the objectives, outlines, etc., etc. And I can share it with you on the chat. And also the MRE, which is more basic in 2 modules, each module 2 day. The next session will be in June and also in November. And you can of course verify the other sessions if you are interested in seeing. So let me share with you this catalog of training also. And the interesting thing is that all of them are known by Calliope. It's the French organization, or AUSIM. So, and also, for example, for SACNAS for the South Africa. So if you want to use the point credits for your emancipation, it's possible. Back to my presentation and come back to the question of, I didn't answer all the questions. So yes, we can use machine learning, and about your second question, Olivier, might we also see classification articulated into formal workflow within? In fact, we have it already. In fact, we have all the elements for classification, and the last step is only a tiny calculator to apply a threshold. So I would say that it is already inside as it is now. No need to further development. And about the formal workflow, it could be discussed. Why? Because depending on the mineralization type, we might have different opinions about it. Thank you very much, Olivier, for your question. If you think that we need to discuss about it further, do not hesitate to contact me. Here is my email. You have my email here, so I will be happy to talk about such interesting subjects with you. Sergio, first question: how do you choose the size of the super block? I think it's related to the